All right, so this class, we're going to basically finish the risk assessment and hydrology. Okay, so in terms of the reading assignment, as I said, please read over the chapter 7, which is hydrology part. Okay, so for the ecosystems and risk assessment, those are mainly about the definitions. So we don't want to focus too much time on that. So if we just do a quick recap of our last class. So last class, we finished up the introduction on the mass balance. So specifically, we talked about the difference between the PFR and the CSTR, right? So although both of them are flow reactors, their performance differs quite a lot. So we know that for first order reactions, one of them is more efficient. It turns out that the PFR is more efficient, right? So to just quickly check whether you guys still remember the question, remember the answer of this question, I'll launch a quiz. So why is a PFR more efficient, right? Okay, 5 more seconds. All right, we'll stop here. It's nice that almost all of you got the correct answer. Okay, so it's because the PFR concentration gradually decreases, right? And that's why you can have a higher reaction rate for the, let's say, the pollutants when it first enters this reactor here, right? So last class, we also talked about the ecosystems. So we introduced some concepts on the phototrophs and chemotrophs, right? So phototrophs are basically the plants, right? They rely on the solar radiation. Chemotrophs rely on other living organisms. So basically they convert chemical energy in chemical components into energy instead of the solar energy. So in terms of the respiration or the type of the respiration, there are aerobic respiration, anoxic respiration, anaerobic respiration. So normally we refer, we discuss the respiration for microorganisms, right? Or sometimes we specifically mention their respiration type for bacteria. Okay, so we mentioned that most of the bacteria are aerobic, which means that they rely on oxygen to sustain themselves. So anoxic means that they don't need oxygen, but they need nitrate or nitrite. So basically species that contain nitrogen inside. And then there are anaerobic types, which means that they cannot live in the environment with oxygen or nitrogen. Okay, so basically they cannot live in this environment. So an example is the yogurt bacteria. Right. So also discuss the concept on the bioconcentration, which means that some chemicals, their concentration might get higher and higher, get accumulated as they are passing through the food chain. All right. So we spent a little bit of time at the end of last class talking about the nutrient cycles. So generally, we're interested in carbon, nitrogen, phosphorus, right? And then the sulfur, okay? So for carbon cycle, it was quite straightforward. So basically, plants do photosynthesis, right? And then there are respiration from all the animals. And then also we mentioned that the fossil fuel combustion is a major source for the carbon on our Earth, right? So if we just break it down into the numbers, right? So this is showing the emission or the capture of the carbon dioxide over the year of 2007 to 2016. So basically it's almost 10 years, right? So you can see that the emission from the fossil fuel industry is much, much higher compared to other sources or sinks, okay? And this is also the reason why we get a large accumulation of the atmospheric growth for the carbon dioxide. You remember that Killing curve, right? So It has been always increasing, right? So we mentioned that from, or in the past 60 years, it increased by almost 30%, right? Which is a quite phenomenal increase if you compare how long our Earth has been in the universe now. So another reason why the atmospheric growth is very large is because of the small Henry's constant, right? Because Henry's constant determines how much of the gas species are going to get dissolved into the water. So because it has a very small Henry's constant, so most of them are actually getting accumulated in the gas. So further about the nitrogen or phosphorus cycle, we should say that maybe the human activities is posing a fewer or less impact compared to the carbon cycle, right? So a lot of them involve the process that's happening in the soil. So in the soil, there are a lot of bacteria. So these bacteria, some of them are anoxic respiration, using anoxic respiration, which means that they can utilize the energy in the nitrogen to sustain themselves. Okay, so for example, for the nitrogen, they can use the bacteria to go through this denitrification and leaching process. Okay, so they can convert from different states of the nitrogen. For example, nitrates is NO3, right? Nitrite is NO2, and then ammonium is NH4. Okay, so they can convert from different states or different chemicals of the nitrogen to extract the energy from that process. All right, so this is, I would say the nitrogen cycle is affected by a lot of the process in the soil. So the same thing applies for the phosphorus cycle. So inside the phosphorus, we also have these bacteria or small animals that's in the soil that can convert phosphorus into different states. But one quite important source of the phosphorus, which is in the form of phosphate ions, they're actually coming from the rocks. So we know that the rocks can basically contain these sources. For example, there can be iron phosphate. Let's see. All right. So basically, there can be some of these chemicals that can get dissolved from the rock, right? When you remember, there's a dissolution or the KSP, right? The solubility product. So for a lot of these chemicals, they can get dissolved into the water and then further sent into the water body, right? It can come from the rain, right? And then mixed into the river and then into the lakes. So for phosphorus, I would say the rocks are actually playing a quite important role in contributing to this cycle here. And then the last one is the sulfur cycle. So for sulfur, if there's no human activity, then the sulfur cycle is not a very important cycle. But because humans are actually contributing a lot of sulfur onto our Earth, we have to introduce how these are being affected. Okay, so there are some major activities or human activities can contribute to this sulfur content on our Earth. So for example, the use of sulfur containing compounds, for example, the fertilizers. Okay, and there can be sulfur dioxide emission from the power plant. So basically all the fossil fuel combustion, let's say even your car engine, right? There can be some trace amount of sulfur in the gasoline and then further pollute the atmosphere, all right? And then there can be acid mine drainage. So there can be pyrite. So basically pyrite is basically a compound of iron and sulfur, right? And they can get dissolved into the water and then further get oxidized, right? Basically it's contributing sulfur into the water body. So a lot of these human activities are actually contributing to the sulfur, and then they can also affect the sulfur cycle, right? So these are about the different types of the nutrient cycles. So the last concept in the ecosystem chapter is the population dynamics. So people use this process a lot when they're trying to introduce different types of bacteria into the wastewater to basically purify the water. Okay, so for example, if you think about a polluted stream, and then we're building a wastewater facility, right? So we know that to remove these organic pollutants in the water, we have to introduce some bacteria inside, right? So how do we maximize the pollutant removal efficiency? We have to introduce certain amount of bacteria so that they can populate themselves in the wastewater, and then they can remove as much as they can. But you don't want to put too much of it. If you do put too much of the bacteria inside, then there will be competition, right? The population will still go down. So you have to find this optimum point where you can generate a large population of the bacteria to remove these organic pollutants. And this is what happens if we introduce the bacteria into a let's say a reservoir that has limited amount of nutrients. Okay, so what happens is for this type of bacteria at the beginning of the time, right, and then there can be a very small number of the bacteria. So normally it needs a lag phase or a period of time for the bacteria to sustain themselves in this new environment, right? They have to see whether this environment is good for them to populate, right? To generate more numbers. And then they realize that, wow, this place is filled with nutrients, right? So they can start to populate themselves. And then you can have this accelerated growth phase. Basically, it's the process that's starting from with the basically a flat number in the bacteria themselves. And then it started to change in its number. And then you have this curve here. Okay, so this is the accelerated growth phase. And then they're going to go to the phase called the log growth phase. So basically, in the log growth phase, you see this is a straight line here. But if you convert this Y scale into linear scale, then what you're going to see is an exponential increase, right? So this is because we're plotting it into a log scale. So that's why you see this is a straight line here, which means that their number is increasing very rapidly, right? So quickly from a few thousands to hundreds of thousands. And as we said, this reservoir has limited amount of nutrients. And what this means is that they cannot populate endlessly, right? And there can be a stationary phase where the number of the newly generated bacteria is equal to the number of the dead bacteria. So they're kind of in a semi-equilibrium, or they're in a steady state, right? And finally, because the nutrients are being depleted, so their number are going to go down. So this is a death phase. So if I ask you which phase we should use to treat our wastewater, okay, so what amount of bacteria should we provide it to the wastewater? We should either choose the log growth phase or the stationary phase, right? Because these are the conditions where we can have the maximum amount of the bacteria to help us remove the pollutants, right? So we don't want to introduce very few amount of the bacteria, mainly because they need a long time to sustain or to get accommodate or get adapted to this environment, or we don't want to introduce them during the death phase. It's a cost of money, right? So these are the basic concepts in the ecosystems. So regarding the risk assessment, I just have a very simple slide that's going to give you, basically it's two definitions, all right? So one definition is how to evaluate the risk, okay? So we hear the word risk quite many times. There can be risk from car accident, can be risk from, let's say, cancer, or can be risk from chemicals, ingesting some chemicals, or can be toxins in our water. So a lot of risks, okay? So how do we evaluate the risk? We cannot say it's very risky, but how risky, right? Is it 100% of deaths, that type of risky, or is, let's say, 1% of deaths, that type of risky condition, all right? So there's a simple way to calculate or to evaluate the risk. So for example, if we want to evaluate the risk of cancer, okay, so what we're going to do is we have to rely on data regarding the deaths that's caused by the cancer. All right. So for example, here it's using the data for the death number in the U.S. in 2001. Okay. So in the year of 2001, there are 3.9 million deaths in total. Okay, in the United States. So among these 3.9 million, there are around 540,000 deaths coming from the cancer. Okay, so in this way, to evaluate the risk, then we just divide these two numbers. Okay, so the risk of dying from cancer in a lifetime. Okay, so that's going to be just the ratio of these two numbers. And then you can find that the number is 0.14, which is 14%. Okay, so it is quite risky in terms of all the diseases, right? So people can also evaluate what is the annual risk. So the annual risk of the cancer is going to be the lifetime risk divided by the estimated lifespan of a human. So what we can do is we can assume the average lifetime is 75 years. Okay, so what we do is we just divide this 14% by the entire lifetime, and that's 0.002, or it can be 0.2% in terms of the annual risk of the cancer. Okay, so this is basically how we evaluate the risk associated with certain activity. But from cancer, it is quite straightforward because we have the data. We have the data that's related to the deaths caused by the cancer. So the same for the COVID, right? So we can basically use the data or the deaths related to COVID and then divide that by the total number of deaths for the last year or until now to evaluate what is the risk, okay? But there are a lot of species there are a lot of conditions where we cannot use these data, or the death is kind of like an ultimate state, right? But there are some species that we don't know, and they're not directly causing the death, right? It may be a lifetime accumulation, or what we call them as chronic effect. It's not acute effect, right? A chronic effect. So how do we evaluate that? Okay. So and this is regarding the risk of a chemical. Okay, so for example, the water quality treatment that discuss a lot about different chemicals or different organics, how they're being risky to human lives. Okay, so that involves the identification of the hazard. Okay, to determine whether the exposure to a contaminant will increase adverse effect to human and to what level of the severity. Okay, so for example, if we found there are lead in the water, so how do we evaluate the risk associated with lead? Because we don't know, or we don't have the death data regarding the lead ingestion, right? So an easy way to evaluate the risk of this chemical is to do animal test. Okay, so although it sounds quite brutal, but we have to do that, okay, to understand how they're going to harm the human health if we accidentally ingest them. Okay, so we have to rely on these animal tests. It can be different types of animals. And what people are trying to establish is a dose response evaluation. So we're going to provide different dose of these chemicals to the animals and then see what is their response. And the most direct response is the death. Okay, so whether that's lethal or not. All right, so basically what we want to generate is the relationship between dose and the incidence of adverse reaction. And here it is the death. All right, so the curve or the relationship is generally shown on this curve here. So on the x-axis is dose, On the y-axis is the percentage of deaths. Okay, so generally, for example, if we're talking about lead, then what we can see is, let's say we're going to use a bunch of lab rats, and then we inject or let them ingest some of the lead inside, or different dose of the lead into their body. Right. So what we can see is they're going to show a curve that looks like this. Okay. So there are some animals that do not have a very good tolerance for the lead. So they are going to become dead uh, at a small dose of the chemical. Okay. So there are some animals that are actually quite endured, quite healthy, or they can basically bear with this higher amount of the dose. So they are going to become dead at the larger dose here. So at the same time, in terms of dose, it's not directly shown as the mass of the chemical. It's shown as the mass divided by the body weight of the animal, okay? Mainly because the smaller animals, they cannot ingest a large amount of these chemicals. And larger animals, they can, because basically the chemicals are going to get distributed within the whole body, right? So it's going to be the mass of the chemical divided by the mass of the body weight. Okay, so we're going to see a curve that looks like this, right? So generally, this curve follows the Gaussian distribution. Okay, so you may have the question, normally the Gaussian distribution looks like this, right? So this is, so this curve here is basically the integral of the Gaussian distribution, right? So the Gaussian distribution, let's say if we use this curve to represent the dose response relationship, then it's still showing that a small fraction of animals, they cannot endure a small amount of the chemical. And there's also a small amount of animal that can endure a large amount of chemical. Okay, but for this curve here, it's showing the cumulative death that's caused by the ingestion of this chemical. So for this curve here, we have to identify a very important parameter. Okay, so this parameter is called LD50. So LD50, so LD here, it means lethal death, lethal dose. Okay, so which is causing the death of these animals here. LD50 means the dose that's correspond to 50%. Okay. That correspond to 50% of the deaths for all the test animals. Okay, so let's say here, all the animals are dead, right? This is 100%. So LD50 is the amount of dose that caused 50% of the deaths. Okay, so this can generally show an average level of the chemical that's putting a lethal threat to the animals. Okay, so now if I have the question, okay, so does a LD50 or does a large LD50 means it's less lethal, or it means it's more lethal? So let's show this quiz here. All right. So this question is asking, a higher LD50 means is the chemical more lethal or is the chemical less lethal? Okay, 5 more seconds. All right, we'll stop here. Okay, so most of you have got the correct answer. Okay, so the chemical is less lethal. So a higher LD50, just think about an extreme here. Let's say if the LD50 is, let's say 50 kilogram, okay? I would say that it's even heavier than the daily water ingest by human, okay? So if even ingesting 50 kilogram is corresponding to the death of 50% of the animal, it means that it's not, it's less lethal, right? It's I wouldn't say that it's not lethal at all, because you still cannot ingest infinite amount of them, right? But the chemical is less lethal if it has a higher LD50. Okay, so these are the basic concepts that I want to point out for the risk evaluation. So we want to come up with a way to assess the risk, right? To calculate what is the risk of certain activity or certain chemical. And also we want to conduct experiments to find out what is the risk of a species or of a chemical here. So that's why we established this definition of LD50, right? And then to show what is the risk of different types of chemicals, right? So that's all for the risk assessment. So now we can focus our time on the hydrology, all right? So I know that you guys did the hydrology lab last week, right? So that is mainly about um, uh, um, the conductivity. So basically how much or how fast the flow can go through a certain filtering media, right? You can use different types of sands, right? To find out actually the water is going to flow quicker, or the flow rate is going to be larger if you're using a material that has a larger porosity, right? So the hydrology in terms of this entire subject it deals with the occurrence and distribution of water on the earth, okay? And the application of the hydrology will help answering the question of how much water can be expected at any particular location and time. Okay, so we know that human have to, or all the animals have to rely on water to sustain ourselves, right? So we want to know what is the distribution of the water at certain time and at certain location, right? So it can help with the setting up the water treatment facility and provide or distribute the water into households. All right. So the application of the hydrology, it's mainly about two sides, right? So one side is the ensure the adequate water for drinking, irrigation, and industrial uses. So this is for the water treatment, right? And then also to prevent the flooding. And a lot of these are associated with the wastewater treatment. So for example, if when we try to urbanize an area, right, we have to consider what is the drainage for the water. So we don't want to, let's say if there are severe precipitation, severe rainfall, we don't want to create flood within the city, right? So we don't want to change the soil structure a lot. And we actually want to evaluate the soil properties to see how easy the water can flow by them, right? So if they're too dense, then it means that most of the water will just get stored in the city, right, instead of getting drained. So further, in terms of the subjects, subtopics of the hydrology, there can be surface water hydrology and groundwater hydrology. So in this class or in this course, we're mainly going to deal with the groundwater hydrology. Okay, we want to evaluate how fast the water flow underground, right? To basically to see what is, let's say if we want to dig a well, right, to extract the drinking water, right? So how much water we can extract from them? What is the maximum flow rate we can extract from the well? And also if some pollutants gets into the soil, so how fast are they going to get dispersed inside the soil before it reach to the, let's say, the residential area where people might ingest these pollutants. So similar to the ecosystem where we introduce a lot of cycles. So for the hydrology, there's also a cycle called hydrological cycle. So basically this is a cycle for water, okay? So in terms of the source of the water, we know that the Earth is mostly composed of water. So we have a huge ocean, several huge oceans. And in terms of the fresh water, we have the basically tall mountains. There are a lot of ice inside, right? And also the Antarctica, a lot of ice in that area as well, right? And also the precipitation, rainfall or snowfall, they can generate fresh water, right? And then after these fresh water get onto the continent, what happens is that first they'll flow by the soil, right? So because we human are living on the ground, living on the soil. But what happens for the water is that the water is not going to just stay in the soil here. Okay, so what happens is they can further get inside, get deeper into the soil. So what we call this process as the infiltration process. Okay, so basically the water will get flow down, but at the same time, there are still some moisture, right? Because the water can get attached onto the surface of the sand, or let's say on the plant, right? So not all of the water are going to get deeper down into the ground, okay? But further, if we just look deeper down in the ground, we call this portion of water as the groundwater. So here, or we also use the term that we also describe this layer of water is the saturated water or the saturated soil. Okay, so what this means is that in this layer of the groundwater, there can be no water adding inside anymore. Okay, so basically this is the maximum amount of water that can get stored. So anything, let's say if you happen to have more rainfall going over this area, right? If we have more rainfall going over this area, then what happens is they cannot get further deeper into the soil by infiltration. So the water will just flow by the surface, right? And then get into the, let's say the lakes, streams, and so on. Okay, but at the same time, let's say if there are no occurrence of these extreme conditions, right? So let's say there are just groundwater, this layer of groundwater, and then we happen to have a geological condition where we have a dip in the continent. Okay, let's say we have a dip in the continent. Right. So because this groundwater or the saturated soil is higher compared to this dip or the bottom of the dip, what that means is the water in this soil are going to go this way and create the lakes, rivers. So this is also the reason why we see so many lakes or rivers on the continent. This is mainly because the saturated soil are generally higher compared to the bottom of these dips, right? So basically water can come out and then these fresh water can form these lakes, creeks, or rivers, right? And further, if we look towards this direction, we know that this is the ocean. So ocean contains a lot, I mean, almost all of the water, right? Around 98%, right? So the groundwater can further flow into the ocean and then just get mixed in the ocean. And also on the surface of the ground, because for this layer, this top layer, which is the unsaturated soil. So the unsaturated soil also contains some water inside. So the water can come out and then go through the surface runoff and also mix into the ocean, right? So this is how the fresh water basically get infiltrated into the soil, and then it can form lakes, rivers, and then further mix into the ocean. But at the same time, you have this huge amount of evaporation, which is generating these fresh water again, because the salt are not going to get evaporated, right? So they can form clouds and then further form these rainfall. And this is a continuous cycle for the water on our Earth, right? So in terms of the mass balance of the hydrologic systems, so last chapter or for the past few classes, we have been talking about mass balance, right? So if we want to build a mass balance for the hydrological systems, we should also list out the equation: accumulation equal to in minus out minus reaction, or plus or minus reaction, okay? But for water, there's probably no reaction that can form water or form a large amount of water, right? So you may think about the hydrogen and oxygen getting combusted into water, but I think only human will do these experiments, and this happens in a very, very little amount of scale, right? So what that means is the reaction, we can probably just ignore it, okay? So for the hydrologist, the mass balance they're going to use is just the accumulation or the change of the storage equal to inflow minus the outflow, right? So as we said, the assumption is that there's no reaction of the water, and also the density, pressure, and temperature of the water do not change, okay? So actually, we can just give an example of how do we apply this mass balance here. We will not solve this problem, but just to try to look at the scale of this problem. So we're trying to analyze the basically the change of the height for or the depth of the water of a lake. Okay, so if you consider all of these sources and sinks of the water, so there can be rainfall going into the lake, right? And there can be the infiltration, right, further into the soil, and there can be surface runoff, right? There can be rivers getting into the lake, and then also the lake will have an outlet, right? So there are different types of input and output, inflow and outflow, okay? So for example, for this problem, we're looking at a lake that has a brook as an inflow, right? It has certain flow rates here. So at the same time, it has an outlet that has an average rate of this value here. For a lot of the lakes, these values would not match each other, mainly because there are evaporation as well, right? So on the lake, the water also going to get consumed because of the evaporation. So it was estimated that the evaporation rate was around 20 centimeter per month, right? And transpiration. So what transpiration means is the plants that's living on the lake, they can also use the tiny spores in the plant to basically pull the water from the lake into the atmosphere. Okay, so it's different from the evaporation, which is just the movement of the water vapor. But transpiration means that it uses the plant systems to pull this water out. Okay, but here we can ignore the transpiration because there are few water plants on the shore of the lake, right? So there are precipitation as a input into the lake here, and then the seepage is negligible. So this is another sink for the water, all right? So and also the surface runoff is negligible. Surface runoff just means that water may get escaped from the lake from the surface of the land, right? So if you know the depths of the lake at certain time, you can use all of these information or use the mass balance to estimate what is the average depth at the end of this month. Okay, so for a lot of the environmental engineers, we have to deal with these problems, let's say, to evaluate the depths of certain certain water body within certain natural resources, right? So there are concepts about the watershed and divide. So watershed just means, or watershed or basins, just means a larger system of water that includes lakes, rivers, the surrounding land, and even the groundwater. Okay, so basically it's an area that generally has a lower altitude or a lower height, right? So you can have a land or the surface land area, you can have mountains here, right? Let's say there are tall mountains surrounding this area. Okay, so we know that the water can only flow this way, right? So the water inside the lake or river here, they're not going to flow upwards. So what we call this system from here to here is going to be a watershed or the basin, okay? So with the definition of the basin, we also have the definition of the divide. So the divide is basically the boundary of the watershed. So normally it's just high mountains, tall mountains, right? With the highest elevation surrounding the watershed. So here it's showing the divide, different types of divide in North America. So you can see that there are tall mountains at the west, right? So there are a few divides in Canada at the boundary between the United States and Canada, and then at the East Coast as well. So these divides actually separate the North America continent into different watersheds or different basins. And when we analyze the water quality or the water transport, we can just look into the water properties within each of these basins, right? So here I'm showing some pictures about the divide, okay? So they even put the landmarks, right, to show that this is a continental divide. So all of these divides are associated with tall mountains, right? So similarly here as well, right? You see this continental divide. So next time when you go to some national parks and see this sign here, you know what it means by divide, right? It's basically separating the water bodies into different watersheds. So there's a definition called the hydrograph. So hydrograph is just a chart that shows the flow rate of water as a function of time, okay? So this hydrograph can be used to describe a certain drainage, can be used to describe a river or a creek, right? So it basically plots the, as it says, the flow rate as a function of time, all right? So as I said, for the hydrology, or especially the calculation of the hydrology, we will just focus on the groundwater. So this is kind of like a zoomed in picture regarding hydrological cycle. And here we're just focusing on the land surface, okay? So not on the clouds or the precipitation, right? So what happens is, similarly, we have the water that can go to the go through the infiltration, right? It can go down to form the groundwater, right? So you have the unsaturated zone or the unsaturated soil at the top of the ground, and then you have this saturated zone of the groundwater. So there can be no more water in the soil here. So because the soil are at higher altitude, right? So if you further go down to lower altitudes, then you have this water actually flow into basically from out of the soil into the lakes, right? So it's basically a stream that's formed by the groundwater discharge, right? So because of that, in terms of the total amount of fresh water, okay, so you can see that basically the groundwater amount is much, much larger than the surface fresh water. For example, the lakes, rivers, and actually the reason why we have these lakes, rivers, and creeks is because we have saturated zone of the groundwater, of the ground, right? So furthermore, what we need to point out is that for the soil, it's basically, if you just analyze what is the structure of the ground on our Earth, right? So it's not pure soil all the way into the center. Otherwise, the water is just going to infiltrate all the way in. So what happens is the soil just composes a very thin depth or very thin layer of our Earth, okay? So below the soil here, normally that involves this confining bed. Okay, so you have a confining zone where the rock here, they basically don't have any pores. All right, so the water, there's no way that the water can further go down here. Okay, so that's why you have this saturated zone, because water cannot further go down, cannot further go through the infiltration. Right, so you have the trees at the top, right? And then you have an unsaturated layer of water, and then you have a saturated layer of water. So because of that, for the for the groundwater, we have confined and unconfined regions, right? Basically to define the saturated zones and unsaturated zones. Okay, so for example, we're talking about this confining bed. So for this confining bed, there's not always a flat layer. So there can be layers that just look like this. Okay, so you can have confining layers that has this type of shape. Okay, so if they have this type of shape, then what that means is the saturated layer or the water here, there's no way they can flow out. They cannot go further higher up or go down. Okay, so finally, the only outlet is go to mix with the ocean. But what this also means is that if we want to find underground water, what we can do is we can just dig a well and then basically reach to the confined layer. And then if the well has a height that's below this top layer here, okay, if it's lower than this layer, then we're going to have automatic water coming out because it's the pressure of the water, right? So the water here is basically compressed or confined, and you can have these fresh groundwater coming out. So that involves the designs for different types of the wells. So I have a schematic diagram here. So what we want to focus on is the hydrologic gradient, okay? And also the hydrologic conductivity. So that describes how fast the groundwater flows, basically in the soil, right? So generally, if you consider the saturated layer, so the height of the layer is going to decrease. And this is mainly because the altitude of the land is always going to decrease, right? You have the tall mountains and then it's going to decrease towards the ocean. So you're going to have this, this difference of the height here. Okay, so people normally measure this height from the bottom of the, what we call the datum plane or the confined layer of the stones. And we can measure the height. We call this height as the hydrologic head, okay? So because of this difference in the height, we can calculate a gradient, which is H2 minus H1 divided by L. L is the distance between these two locations. And we call this as the hydrologic gradient. So actually it's a hydrologic gradient that leads to the velocity, leads to the flow of the groundwater, okay? So how do we calculate the flow of the groundwater? How do we, let's say here is an example of how to calculate this hydrological gradient, right? So if we have H2 and H1, one is 8 meter, one is 7.8. We know that the difference of the height is basically 0.2 meters, right? And further, we divide that by the distance, 40 meters. You can see that the hydrologic gradient is 0.005. So we can also have the hydrological conductivity. That means how fast the flow or the water can flow from this medium here. So we can evaluate what is the velocity of the water in this medium here. So what we do is we just multiply hydrologic conductivity by the hydrologic gradient. And what we get is just the velocity. Okay, so here, sorry, I have to go over this very quickly, but you can see that this is all very straightforward definitions. So for example, if we're talking about that two well system again, so you remember that 0.2 meters of the height in difference, divide by 40, that's the hydrologic gradient. So we can use this Darcy's law. So basically this is called Darcy's law to calculate what is the velocity, right? So we just multiply this gradient by the hydrologic conductivity. So the conductivity is here, and we can find out that the groundwater velocity is this value. And then further, by multiplying this value by an area, we can calculate what is the flow rate of the groundwater, okay? So you're going to have maybe 2 or 3 homework problems to practice this. So I do want to mention that the hydrologic conductivity is a part of our exam, okay? So further, there are some simple slides about the how the Darcy's velocity differ from the actual velocity of the water. But this is not going to be a part of our exam. So we can probably talk about this in our next class. All right. So finally, I want to say something about the exam. I would say we should focus on the homework and class notes. Okay. Although I give reading assignments of the textbook, please don't use all your time to read the textbook. Okay. So what I want to say is that if you can work out your homework problems without any problem, you will get a full score. Right. So this is the way I typically give exams. It's going to be about calculation, some definitions, but those definitions are in the basically they are already taught in our class in the class notes. So this is closed book exam. So 1 page of notes allowed, and it's going to be happen. It's going to be the regular class time from 11 to 11:50. So I will make the exam paper available on Canvas at 10:59, 10:57, and then you should upload by 11:55. Okay, so try to submit in time because I will deduct points for sure for the late submissions. Okay, also try to make sure that you have internet connection. So to please keep your web camera on during the exam. I think this is the same requirement for all the other exams. So send me a private chat if there are any questions. So I would say these are the general rules for the exam. But in terms of preparation, if you want to get a higher point for the exam, focus on the homework problems. Okay. And also let me or the TA know if you have any questions about the homework. Right. So that's all for the contents of this class. I will see you all on next Monday. All right.